First of all, sorry for the delay, and welcome for the talk on machine learning, applications of machine learning on combustion engine. This is a talk organized by the SDAIA-KFUPM Joint Research Center through the KICS platform. We have our presenter today, Dr. Balaji Mohan. Dr. Balaji is a lead scientist at Saudi Aramco, Iran. He did his PhD and his postdoc from the National University of Singapore. And then he worked as a postdoctoral fellow in the Clean Combustion Research Center, where he works on developing combustion systems. And he also has worked significantly on combustion engines. And he leads the effort in the fuel technology division at Saudi Aramco, especially working on AI and implementation of AI in the field of IC engines. We are very glad to have Dr. Balaji here, and I will now forward the talk to him. So, thank you.
Thank you. Good afternoon, everyone. Today, my talk is going to be on how is AIML changing ICE optimization. So, a small brief introduction about me. I was born in Chennai, which is in the southernmost state of India, where I did my bachelor's in engineering. After my bachelor's, I joined Delphi TVS as an application engineer, where I worked on optimizing engines for Mahindra & Mahindra, Tata, and few off-road vehicles as well. And then I moved to Singapore to do my PhD in mechanical engineering, specializing in combustion science from National University of Singapore, where I also had an opportunity to work as a postdoc for another 2 years in an air conditioning project. So I decided that air conditioning is not my field, so I just want to move back to combustion. So I had an opportunity of a postdoctoral fellow at King Abdullah University of Singapore, King Abdullah University of Science and Technology at Saudi Arabia, where I joined as a postdoc, and then I continued my combustion research there, predominantly on sprays and numerical simulations, before joining Aramco as a lab scientist in early 2020. So my research profile can fit into any of these 4 quadrants, which is predominantly the fundamental research on experiments, simulations, and then applied research with experiments and simulations, where I performed some characterization of sprays and spray combustion. This I did both at NUS and King Abdullah University of Science and Technology. And then I also worked on spray simulations, where I developed a cavitation-induced spray model to capture the spray behavior very well with simulations. And then I also performed some in-nozzle flow simulations. This work I did at NUS and then carried forward it to KAUST, and then also in my early days of Aramco, I did this work. And then I also involved in engine optimization at Delphi TVS, and then also in NUS. And also I have done some engine simulations to optimize its performance and emissions through simulations. I have done this kind of work at NUS, KAUST, and then also at Aramco. So the research focus, I like this quote very much from Takashi Suzuki, from his book called The Romance of Engines. I prefer to everyone to read this book if you want to take internal combustion engine knowledge in a lighter note, where he says that our ultimate goal is to create an engine that functions in harmony with nature while still meeting the demands of an ever-advancing civilization. So with that in mind, our main focus is to improve ICE performance and emissions. All along until my second postdoc, I was trying to do it with fundamental research, combination of experiments and numerical simulations. When after I joined Aramco, I'm trying to do it with the 4th element called AIML. So coming to the main agenda of today's talk, I'll be walking you through the motivation and then AIML framework for ICE optimization. And then we have developed an in-house AIML tool. I'll walk you through it, and then I'll I'll explain the ICE optimization through 3 different case studies, and then I'll summarize my talk. So coming to the motivation, we all know that the industries are evolving from industry 1.0, which started in 18th century, to until today we are at industry 4.0, where the factories are becoming smarter and then using autonomous systems and then IoTs, Internet of Things, and artificial intelligence. So we have to keep in pace with the industrial need. So this industrial revolution is bringing us many advantages like increased productivity, increased process efficiency, enhanced decision-making, greater work safety, and improved competitiveness. And Aramco trying to implement IR 4.0 industry-wide in various segments of its businesses, like manufacturing, connectivity, and computing. And one of the main objectives is to implement AI and data analytics into our business stream. So keeping this in mind, we have been trying to focus our vision towards the business needs. So we are trying to do something in line with the Aramco's vision of implementing IR 4.0, where we try to use AIML to optimize our internal combustion engines. So before getting into the framework, let's see how the evolution of optimization of internal combustion engine has progressed. It all started with manual optimization, where we will have a few designs or few calibration parameters. We tested out the engine and then we optimize with those 1 or 2 combinations of designs and calibration parameters. And then with IT advancements, we went on to use statistical tools like DOE, design of experiments, where we went further to have a little bit more design parameters. As with improved computational power, we were also using genetic algorithm like optimization codes to optimize our internal combustion engine. And today we are in the digital era, where we are trying to capitalize all the data that we have in the past, so we can use that data efficiently to optimize our engines today by using the machine learning. And tomorrow, what we envision, and then what is the industrial need, is that we will use different elements of artificial intelligence and IR 4.0 to optimize our engines further to better performance and emissions. So when we talk about optimization of IC engines, it is of 3 categories. One is geometrical category, where we can optimize the piston bowl geometry or the pre-chamber geometry, injector characteristics, or intake exhaust ports, or even stroke or bore of your engine geometry. And then when it comes to calibration, these are the control parameters like intake air pressure or temperature, or tumble ratios, fuel ratios, extra EGR, injection parameters, spark timing, etc. And then the third element is fuel, where we can tailor make a fuel to match our advancing technologies, like tailoring their properties like RON, bond, thermophysical properties, volatility properties, and flame speed of the fuel. So to do this, we have developed our own AI-based optimization framework, which generally starts with building a test matrix using design of experiments. And you can see if it is a geometrical parameter, we vary the geometrical parameters with the DOE fashion. And then if it is a calibration parameter, we try to fit the test matrix with a uniformly distributed in the design space. And then we generate the responses of these test matrices either through running experiments or simulations, so that we get the responses for each of the input from the test matrix. And then we do our data processing or engineering the features, where we get rid of the outliers, and then we try to find the correlation between the inputs and outputs. And then we use our machine learning models to train on the data set that we generate. And then we use our global search optimizers to search for the global optimum within the response surface that we create with the machine learning model. This machine learning models can also be used as a surrogate to the experiments or simulations, where we can scan through millions of design space where there is no experiments or simulations available. So we get a few potential candidates. We validated them through either experiments or simulations. We run the entire process. This process is an iterative process, which we call active learning process. And at the end of this entire framework, what we get is an optimized engine performance and emissions with reduced time or cost of calibration. So in order to realize this framework, we have developed our own in-house AIML tool. So as I said, there are three key elements of the framework. First one is the design of experiments, followed by the machine learning algorithm, and then the optimization. So we put everything into our in-house AIML tool. When it comes to design of experiments, these are the 16 different DOE algorithms that go into our AIML tool, because every algorithm is best suited for a particular application. So we don't want to leave out anything. And this is a small comparison between the commercially available statistical tools, where we were able to capture all different varieties of DOE algorithms in our tool compared to the statistical tools available in the market. And then coming to the machine learning part, we call this as automated SuperLearner or AutoSL, which takes in the data set. And this data set are used to train our base learners. Base learners are big learners, we call them. And then based on those predictions, we use a meta learner to weigh each of the base learners in a linear fashion. And then this meta learner will give out a model called SuperLearner. And this SuperLearner, when we combine it with the genetic algorithm to further optimize their hyperparameters, this framework is what we call as automated SuperLearner, and we have already applied for a patent for this. And this goes into our tool as well for the machine learning part. And this is the AutoSL performance compared to a genetic algorithm-based AutoML already available in the open literature. And we were able to get a very good performance compared to all other different AutoML, as well as with reduced computational cost in optimizing the hyperparameters. So when it comes to optimization, we approach the problem in two different ways. One, attacking the problem as a multi-objective problem, because engine optimization is a multi-objective problem where we have to minimize our emissions and maximize our performance at the same time, with a few constraints where the constraints usually comes from the regulatory body on the emissions part. We use NSGA2, which is non-dominated sorted genetic algorithm 2 type, and we select the best candidates based on a Pareto front in this case. Or we convert the entire multi-objective problem into a single objective problem using a merit function, where we give different weightages for different objective problems. And then we also try to include the constraints into this merit function. And then we again use NSGA2 to optimize the merit function. Here our problem gets simplified by either to minimize or maximize the merit function alone instead of maximizing and minimizing 2 or 3 different functions. So for this particular part, the design space where the variables and its ranges are given as an input, and we also take the objectives and constraints as an input to the algorithm, and then we use the search algorithm to search for the best candidate or optimum candidate. So these are some of the GUI screenshots. This is the tab where you can perform the design of experiments, and then you have a visualization as well, where you can visualize for the distribution of the input parameters in the design space. And this is the machine learning tab, where you can perform the machine learning and also have a rich set of visualization, where you can visualize the heat map and then the response surfaces, and also the outputs like R-squared. And this is the optimization tab, where you can perform the optimization, and you can also visualize how the candidates are distributed in the design space and also in the objective space using a Pareto front. So as I said, we have a framework with us. So we try to implement this framework in optimizing the engine in terms of geometrical aspect or the calibration parameters or for fuel design. So I'll go through case studies on how we have used this tool on optimizing different parameters. So let's see how we used this tool to optimize the geometrical parameters. So we took a case study where this engine is a heavy-duty gasoline compression engine, which with a compression ratio of 17.3:1. It has a stepped left bowl type, and we chosen three load conditions: B25, B50, and B75. And for each load, we had 128 bowl designs. So altogether, we had 324 data points. So for inputs, we have 5 independent bowl parameters and 2 injector parameters, geometrical parameters, and then a swirl ratio, which is again a geometrical parameter of the head. So this is how the bowl is parameterized. We have 5 independent variables to define the bowl geometry and 6 dependent variables based on the independent variables. So we took only the independent variables as our inputs for this bowl parameterization. So for our outputs, it's typical engine outputs like ISFC emissions and design limits like peak pressure rise rate and the peak combustion pressure. So we have all this buzz about machine learning, artificial intelligence, but how it is compared to the traditional way of responsive methodology was done in this work, where we used Dakota from San Diego National Lab as a tool to do the response surface methodology, where the Gaussian models and polynomial models were used predominantly. And for optimization, it was a genetic algorithm-based global and local optimization approach. And for machine learning code, we used our in-house code, which is basically the SuperLearner. And for optimization, we used both the grid gradient ascent and genetic algorithm based optimization. So these are the results that we got. The gray one is a baseline, and the blue is from the DOE data set that we have generated with 128 bowl designs. And the red one is response surface methodology, and the green one is through our machine learning genetic algorithm framework. And we could see that we were able to reduce the soot emissions under all load, and then we were able to maintain the NOx and soot within the criteria pollutant limits with improvement in ISFC, MPRR, and PCP, and then merit function altogether. So this table shows which methodology has the percentage improvement. For example, for 50% load and 75% load, the MLGA was able to give a better performance than the base case, while at 25% load, the RSM was able to give the best performance. So this is how the bowls compared with the best DOE with RSM and the machine learning models. And you can see that machine learning model had a shallower bowl with a shallower and wider bowl than the DOE and RSM based bowl designs. And these are the other properties like injector nozzle holes and swirl ratio and spraying cushion angle, which is very close to the CFD DOE, but with the differences in the bowl shape, we're able to get additional improvement in the performance and emissions. So now, how machine learning is better than RSM? Machine learning model can be used as a surrogate to CFD, where we can use this model to predict the output responses for any unknown input responses. Although we have similar merit improvement from RSM and ML, we concluded that ML is better than RSM for these reasons, that it can act as a surrogate model in predicting the unknowns. And the improvements obtained through ML is unbiased under different loads compared to the RSM, where it was better only in improving the low load performance. So we use the same framework to optimize our calibration parameters. where we had two different strategies. The first strategy is that we started off with the existing data set that was available to us. We fitted our machine learning model to the existing data set, and then we used the genetic algorithm or any optimizer to optimize for the global optimum. This is mainly to see whether we can able to reach the global optimum using this strategy. The second strategy is that we try to improve the development time. So we started out with a set of test metrics given to the experimentalists to run them on the engine and then get us the responses. And we followed the same process, except that we had this active learning loop where we were able to validate them again through the experiments and then we process the data until we feel that we got a global optimum with reduced time and cost of calibration. And very important thing is this entire process involves human involvement in every stage of this framework. So for strategy one, what we call is one factor at a time. That's how experiments are done. We take one factor, we try to sweep between lower and upper bound, we record the responses, and then we go for the next input parameter. We do the same for sweeping it from lower and upper bound. So we call this as one factor at a time approach. And the other one is design of experiments, where we try to vary all the parameters at a time, and then we try to record the responses of varying input parameters. So for both the strategies, we kept the input parameters the same, like rail pressure, start of injection sweep, and then injection pattern, whether we go for single injection or double injection, and then we went for EGR sweep. But for strategy two, we need an additional step where we have not conducted any experiment prior. So we need to apply our domain knowledge to identify the lower and upper bound of each of these parameters. Otherwise, we will end up in damaging the engine. So we need some domain expertise there in selecting this lower and upper prior to the experiments. So this is the approach. We had 6 input parameters, either if we go for one factor at a time or DOE builder to build our own test matrix. We test them on engine, we develop a machine learning model, which is another sub-process where the data set is cleaned and then the SuperLearner is trained. We evaluate the model and then we apply genetic algorithm with hyperparameter optimization, and then it goes into a loop until we get a better model. And this model is used in the optimization as a surrogate to screen the design space for millions of input space. And then we rerun those potential candidates again on the engine, and then we feed back this back to the data to build our better machine learning model in the next iteration. So this loop is continued until we found that this is the best ISFC and smooth we can get from this control parameters. So we had 2 different data sets. One was from the one factor at a time, where engineers' expertise was able to get them to a maximum or optimum region. The other one is based on DOE test matrix. So we want to compare them and then see how the data set is good enough for the machine learning or not. So we used a rain cloud plot. Rain cloud plot is nothing but a combination of box plot, Weiling plot, and the statistical information is also given. For example, the box plot gives you the median by the dark line, and then the interquartile range, which is this bounds of the box, and then the turkey fences, which tells us this is the maximum, and anything beyond this turkey fences are outliers. And then the kernel density is this blue region or the green region, which says how the data set is distributed. And then the red dot is the mean, and all the other points are given as in the plot to see where exactly how many points are lying up in the outlier region or something like that. So this is the comparison of the inputs and the target variables. And you can see that DOE was performing better in terms of outliers when compared to the OFAT. And also we found that OFAT is not covering the design space efficiently, whereas we were able to cover we designed space efficiently with the DOE-based test matrices. And for DOE dataset, we used Latin hypercube space filling method. And we started off with a 36% smaller dataset than the OFAT approach. And then we went on to see how each of the output variables and input variables are correlated with each other. So we plotted a heat map to see what are the correlations. So how to interpret this heat map? If you have a negative value, that means your variables are negatively correlated. That means if your X is increasing, your Y is decreasing. And if it is positive, it means a positive correlation. Both are increasing the same trend. And 0 means they are either uncorrelated or the data set size is insufficient to capture the correlation between them. So interestingly, this was also able to capture the physics within it. For example, the EGR. The EGR shows a positive correlation with the smoke number and a negative correlation with NOx, which is very well representing the physics. When we increase the EGR, we tend to increase the soot formation. While we increase the EGR, we will reduce the NOx. So that's captured very well here. And then the DOE data set was also able to capture the same exact physics, but not with exact absolute values. But it was able to give the same trend with a smaller data set. So this means the DOE data set is equally good in capturing the trends and physics with the OFAT data set, even though it is a smaller data set. So the model performance were actually evaluated using the R-squared plot, where this thick gray line is the ideal fit if all our actual outputs and the predictor outputs are this one and the same. It should lie in this gray line. And this dashed lines are the actual fit, which may deviate slightly from the gray lines because we may not expect 100% fit for any model. And then the points are all the test data sets, where this is 20% of the entire data set that we use for testing purposes. And we could see that from all the outputs, the DOE data set models based on the DOE data set performed well compared to the models based on the OFAT data set. This was our observation, and when we looked into why this is happening, we found that it is because of the poor data quality of OFAT, because it's all intuition driven by the experimentalists. They are very biased in developing this data set. And it was also highly skewed, and it also has more outliers in the target properties. So we went on with a merit-based optimization approach, where we reward whenever we get a better ISFC or emission, or otherwise we just penalize the merit value. This is the merit value that we used, where each of the objective has its own weights, and this is a design factor or a constraint where it is also weight. And if we have a good emission, or we get lesser ISFC, this is always rewarded. That means this function is positive. Otherwise, if we go beyond, a poor ISFC, this becomes a negative, and this merit value is penalized. This is how this merit function is framed. So we used 3 different optimizers here. In this case, it is differential evolution, genetic algorithm, and particles form optimization. And with each different optimizer, we took 2 best candidates for our active learning approach for the next round of iteration. Why do we go for 3 different optimizers? Because we don't want to waste time in figuring the best tuning parameters for each of these algorithms. So when we went on with the default parameters, so when we go with default parameters, each optimizer has its own advantages and disadvantages. For example, the particles form optimizer is quick and converging, but it is not converging to a global value, but rather stuck in somewhere in the local maximum values. However, genetic algorithm and differential evolution were able to further come out of the local minima and trying to go towards the global minima, but it needs more iteration for that to happen. But we are restricting ourselves to 150 iterations. So we go for active learning approach, and then we try to go to the global region from this framework. So these are the optimized engine performances. We were able to get a benefit of 14.7 gram per kilowatt in ISFC while maintaining the emission criteria and design limits of the engine. And these were the optimized calibration parameters. For example, the experimentalist came up with the best calibration parameter by choosing a single injection parameter. But somehow the DOE and the machine learning algorithm were able to find that the best strategy is for double injection and not a single injection strategy. So the key achievements and learnings from this exercise is that we were able to reduce the SFC by 14.7 gram per kilowatt hour with a 40% reduction in the development time, which means 40% less experiment than the one factor at a time approach. And if we apply the same machine learning based approach on the one factor at a time data set, we were able to improve the performance, but with iteration, the improvement is very linear. So, but with the DOE based data set, it was exponential. This is mainly because of the good data quality. We were able to get better machine learning models. That means better and faster outcomes. So, so we are trying to apply the same approach to fuel design as well. So our research objective is to design a fuel design tool, which can optimize the different fuel properties like combustion properties by optimizing its non-flame speed, or volatility properties like vapor pressure, initial and final boiling points, emission properties like heat-soaking index or NOx emission index, or thermophysical properties like density, viscosity, or surface tension. So fuel design can be done in two different ways. One is using high throughput screening, where we get a data set with known properties. We use them for training our machine learning algorithms, and then we import a database with unknown properties, which is much larger in space, critical space. And then we start predicting the properties of interest using the machine learning models that we have trained earlier. And then we screen this database with predictor properties for a potential fuel components or candidates that can be added to the base fuel. This is one approach of enhancing the fuel properties. The other approach, here I want to emphasize that machine learning models are very key in this framework. I'll show you in a couple of slides why. And then the second approach is inverse field design, where we have the target properties given to us, and we have also the constraint like P on a number of components that we can we have from refineries. So we will go with a search algorithm, which calls for the machine learning models that we have developed with the database of known properties, and we have a database of fuel components where we can mix match for the certain fuel properties, and we get a real fuel composition. This is another way of building fuel for composition. So again, here I would emphasize that the machine learning models are very important. Why? Because the chemical space is very big. It's in the order of 10 power 33 to 10 power 60 in the entire planet. And then there are billions of possible C1 to C13 compounds, because C1 to C13 are small molecules, and it's in the billions of range. And there is a database called GDP13, which includes 13 million compounds of C1 to C13 compounds. And we have our own database with known properties, which is a few hundred. So our machine learning model should be very generic in order to predict the properties of millions of compounds from the database that we know, which has only a few hundreds. So this is the literature review, where the machine learning activities for predicting the fuel properties is catching up in the latest years. Like in 2021 and 22, people are publishing more papers using machine learning models to predict fuel properties. And also this plot shows you that the two top algorithms that are being used are supported by machine and neural networks. And recently, neural networks are outperforming the support vector machines because of the advancements in deep learning and other stuffs. So this is a brief summary of it. The dark green is where people develop models for physical properties like density, viscosity, surface tension, etc. And then these are the combustion properties like Ron, Mon, YSI, TSI, CT number, etc. And then people have also tried to combine models for both the physical and combustion properties. These are top 25 papers I could get it from the Scopus, and these are different machine learning models reported in the literature, and there are different molecular representation, including the functional group, branching index, and molecular descriptors in the literature. And people have been trying to predict the properties, various properties like density, viscosity, boiling points, critical volume, pressure, temperature, etc. And one thing that we can notice is that all these people are working on different machine learning algorithms for different properties, but they were scattered here and there. I mean, it's not a holistic view of using machine learning algorithm to fuel formulation, but they are trying to use this approach to predict few of the properties in the literature. So we have developed our own approach where we were able to come up with a few models for the few. This is still work in progress. We were able to obtain machine learning models for combustion and then some physical properties as well. And these are our model performances where we assume that this is good enough for any engineering practice to build a fuel formulation out of this. So how our model is compared to that from the literature, these are some of the properties that are reported in the literature. This is for pure components. This is not for mixtures. This is only for pure components. So you can see R square, if it is higher, it is the better, and mean absolute error, if it is lower, it is the better. And we could see that our model was better than that's reported in the literature so far for the pure components alone. And for YSI, we were not the best, but we were close to the best model. But interestingly, we were better than the deep learning model. But we are trying to apply for a patent for this, so I cannot shed more light on this. But this is not a deep learning based model for that. So I would like to summarize my talk with few slides now. So with engine data and with our in-house machine learning, AI machine learning tool, we were able to improve the IS performance and emissions. In addition, we were able to develop surrogate models for CFD and experiments. And also we were able to go for rapid optimization, which means reduced development time. And these are some of the applications where we were able to use our AIML tool, which gave us better performances and emissions with reduced computational costs if it is a CFD simulations and reduced experimental runs if it is an experimental campaign. And then these were some of our publications till date. We were able to publish with this AIML approach within RNDC engine combustion team. So I would like to take this opportunity to thank my colleagues and collaborators from Aramco, Dara, and Detroit, and KAUST, Argonne National Lab, and KFUPM as well, where a few of the works with collaborator with him. So with this, I conclude my talk. I'm open to take questions. Thanks.
So if you have any questions, please feel free to raise your hand so I can allow you to talk. Or you can type your questions on the on the chat box, on the question answers. Okay, I have a question to start with, Balaji. So you talked about the data set and that there's a lot of experimental bias. And how do you go about retaining some of the experimental points and maybe removing some outliers? So what strategy do you do for that?
We don't usually remove outliers because we always start with a smaller data set where we are talking about some few tens to hundreds of data sets. And it's not very advisable to remove outliers, then we will be limited with the smaller data set to start with. And machine learning models are not very good with the smaller data sets, as you all know. So we take the outliers, which also helps the model to learn that this is not the right way to go for optimization. So the optimizer will also know that this path is not the right when trying to optimize. So we take the entire data set. We didn't remove any outliers.
So if you have less confidence on some experimental measurement, so how do you deal about them? Do you like not include them, or you live with the inaccuracy that comes with it?
No, our experimental campaigns are very robust enough. They just report data only when there is a certain amount of and reproducibility from the experiments. So we believe our experimentalist and then experimental equipments, which are some good standards. So,
but when we develop data sets, we also take a lot of data from the published literature. And
yes.
There's a lot of inconsistencies on those.
Yes.
Yeah.
There we have to. If you get the data from the literature, for example, for the fuel property, many people would have reported. For example, if we take a density for same chemical compound, people would have reported different density values. We take the range. If the range is too big, we remove the outliers, or if the range is very small, we take the average value. And that's how we deal with this.
So I have some questions here from the attendees. They would like to see slide number 29.
Okay.
Okay, go to slide number 29.
You can just type 29 in there. Just click 29.
Yeah. We are 42, so let's.
Almost there, right?
Oh,
So this is not very efficient.
yes.
Yes.
So I think they want to talk about the strategy that was discussed here.
Yes. So the strategy is that we already have some experimental data from our engine test lab, where the existing data is based on the experimentalist intuition on moving towards the optimum region. So they use their domain knowledge and expertise to move towards the optimum region. They have already done this experiment, and they have collected a few data points where we started off with those data points. This is what we call one factor at a time, where they take one input parameter, they sweep within the lower and upper bound, and then they move on to the next input parameter. They do the same, and then they have a good set of data points for one load condition and speed condition. So we use that data set, we trained our machine learning model, and then we try to search for a global optimum from the data set. So this is how we did.
Okay, we have another question from Rohan. What is your future if I'm developing a model? Okay.
You want to get an idea.
Yes.
Run with it.
Yes. So how do I go about developing a model? I think that's what maybe a student was asking a question.
Okay, this is the same question everyone who wants to use AIML in their application have. So that's where we have developed our automated SuperLearner, where it will aid the scientists and engineers with zero or no knowledge on machine learning to use machine learning for their application. So that's where automated machine learning are all coming in place. And we have also developed our own automated machine.
Is it publicly available?
Not yet, because we are trying to patent it.
Okay.
So we haven't.
If the plan is to make it available at some point, or is it just local?
Only for in-house for now.
Okay, we have one more question. How do you define the best model?
That's very tricky question. I mean, you cannot evaluate a model based on one metric. For example, you cannot just evaluate based on your R-square plot, because it may misguide you. And you cannot even evaluate your metric on mean absolute error or root mean squared error, because you need to know how much percentage of experimental uncertainty is there, or you need to know how big is this value compared to your range of data set you have. So it's always go about mix and match of all the metric and see and apply your knowledge, domain knowledge, to see this is good my model or not. So that's how it has to be done.
We have one more question from Sadiq. Can you shed light on how a physics-informed neural network differ than a simple neural network applied to your problem area?
So physics-informed neural networks are, we are trying to use neural networks or deep learning neural networks to capture your physics, with a basic understanding that neural networks can be used as a universal approximator. That means it can even use to solve your partial differential equation or your ordinary differential equation. That's the basic understanding. But this is like a supervised machine learning, where you have a data set, we train on any machine learning model, and we get the response from the machine learning model. That's how I see. And it doesn't involve any physics in developing these models. Pins are different platform. I mean, it has nothing to do with the models that we are dealing with today.
I have a question, if you don't mind. So we talk about a lot of AI or engine optimization.
Yes.
And this is like a general question that people generally have with a lot of electric cars around, and a lot of talk about the death of the IC engine. And we have one group of people say that this is the end of the combustion engine, and we are trying to optimize it and trying to make it better. So what do you tell people who say that the combustion engine is over?
I can see its life is over. I think there are millions of cars still running with IC engines in the roads, and you cannot replace them overnight, right? You cannot replace all the engine-driven vehicles with battery vehicle in overnight. So it has to be slowly replaced, and I don't see it is coming very soon now. And we have more developing nations where they still use IC engines as their prime movers than battery electric vehicles. For example, in India, 60% of energy still comes from the coal power plant, where our grids are not greener than the burning liquid fuels on your IC engines. So there is still potential. I mean, it's not dead yet.
We have a second. First of all, thank you for accepting our invite and joining us today. It's indeed an exciting presentation. You should like it. Everybody's interested. And I'm happy to say, actually, the number of attendees that we have today is one of the highest, if not highest, that we ever had in any of the course. It's close to 100 somewhere. So I'm really proud of it. So two questions. In one of the slides, you reported it was an interesting reporting to me. Some results were reported on an entire data set. And I believe this is not usually a usual behavior for machine learning.
Yes, I think you are referring to this slide. where I was reporting it for fuel.
Yes. Yes, this one
Yeah.
here, yes.
This is because just for the comparison purpose, but we always evaluate our models based on the test data set. The test data set is kind of a holdout data set,
Right.
which the machine learning algorithm has never seen during the training stage. So we always evaluate on the test data set. But here, just for the purpose of comparison with the literature, I used on the entire data set. But although this is high value for R square, I have just reported here, this is all for the data test data set where it is still 0.988.
Yeah, the holdout, we can
Yeah,
the holdout.
so-
yes. Okay.
This is how we do.
Okay, right. I thought there is some sort of practice in this domain where it's acceptable.
No, I mean, that for the purpose of comparison, I did that.
My other question is, you mentioned and you highlighted a very important point related to the limited data. And I think, especially when it comes to your domain of expertise, this is actually you see in other areas, for example, computer vision, you say, yeah, acquire more data, enable this data, and then you may be able to solve that problem in crowdsourcing or something. When it comes to these problems, it's impossible. It's an impossible request to collect that large of a data set, have all the chemical properties and the physical properties and all of these. So we have to deal with limited data in general. Now, I've seen in similar areas where they face this problem, they resort to synthesizing data or what they call pseudo kind of properties, kind of computer generated or simulated. And they use that heavily, and they have shown significant improvement in the results and the generalization of the model. Of course, you still have to tap into or look into basically working on training on synthesized data, then applying it to real data might not be a perfect match, but there are solutions to that. But have you looked into this area? Is there a way to?
I had some kind of GAN to do this, generative adversarial networks. I tried it on RON and MON dataset, but they were not that good because the RON and MON are highly nonlinear. And what I'm showing is for pure components. So with such a small data set, you cannot generalize to unknown chemical compound. So it was not working well for this kind of problem. So we have to live with the small data set and we have to try to capitalize this small data set and then build efficient models. That's how it has to be done for this kind of domain.
What about other paradigms of, and I promise this is my last question, other paradigms of learning, something like semi-supervised or unsupervised or even weakly supervised, where you have a small amount of control, high label, high quality labeled data, and then a large data set of open data that is, has some sort of improvement.
Yes, we also tried to use some encoders and decoders, but it's a work in progress. I was not able to get good data, good results from them. But still, encoders and auto encoders need a lot of hyperparameter tuning as well.
Perhaps this is an area of collaboration between us. I believe we can back to you.
I don't think we have any more questions, and in the interest of time, I'd like to thank Dr. Balaji for spending his time for coming over here and for giving us a very good talk. It was very well attended, and it was very well. We have seen a lot of good results. So thank you for your presentation, and thank you for the attendees for attending the event.